Hi, thanks. Yeah, I'm happy to be here. Thanks for the organizers for putting this all together. So what I'm going to talk about today is something I worked on dealing with. Whoops, is this showing chat at the bottom there? Let me see if I can.
Don't go away.
Oh, okay, good. Yeah, so dealing with some computational experiments in two-cover descent for genus 2 curves, in particular genus 2 quintics. So genus 2 curves with a rational Weierstrass point. So just for background, the setup is that we have, if you have a smooth projective curve of genus at least 2 over a number field, then of course by Folting's theorem, the set of rational points on this curve is finite. The big open problem in this area of, arithmetic geometry, Diophantine geometry is, well, how do we actually compute this set? Well, this is one big open problem, right? And even if we just have a genus 2 curve over Q, currently there is no known method that will, actually provably compute the full set of rational points in general. I believe there's some methods that in principle work if you assume some hard conjectures, but I believe those are also not practical feasible methods. They're very much an in principle algorithm. So what I'd like to talk about today is some experiments in seeing how far we can get with a certain set of techniques in computing rational points on a database of genus 2 curves in practice. So one of the key tools used here is Chabot's method. And this was kind of the state of the art before Folting's proof in proving the Mordell conjecture. And the content of it is, if you embed a curve in its Jacobian using the Abel-Jacobi map at some rational base point, and if the rank of the Jacobian is less than the genus, then, well, the closure of the rational points in the Jacobian are some proper p-adic submanifold of the p-adic points of the Jacobian. And so then you sort of intuitively expect that if you're taking some proper p-adic submanifold and intersecting it with a curve, well, generically you'd expect this to be zero-dimensional, right? And Chabot essentially, the proof is showing, well, yes, indeed, this is the case. When rank is less than genus, the intersection with the p-adic points of the curve is zero-dimensional and therefore finite by compactness. So the reason this is of interest now is because of Coleman's work in 1985, which used p-adic integration and Newton polygons to turn this whole argument very explicit, and to actually give us very nice bounds that are often close to sharp. And if you're lucky, just on the nose sharp, when you take a prime of good reduction and run through Chabot's method. And in many cases, this can also be turned into an algorithm for computing the set of rational points by using algorithms for computing p-adic integrals and all the other stuff associated with this. So for example, in Magma, Brown and Stoll have implemented this for curves of genus 2 and rank less than 2. And I believe this also should work for higher genus hyperelliptic curves with rank less than genus, but Magma can only currently compute Mordell-Weil groups when you have genus 1 or 2. And so that's kind of the obstacle there. So the data set of genus 2 curves that we're looking at here is coming from work of Booker, Seisling, Sutherland, Voigt, and Yasaki. They computed a database of 66,000 something genus 2 curves over the rationals that have absolute discriminant at most 1 million. Heuristically, this database should be near complete. If you look it up in the LMFDB where this database is displayed, you can find something that talks more about how heuristically there's probably a few curves missing, but probably not many. And this is stored in the LMFDB with lots and lots of pre-computed data, including a set of rational points. Now, for curves of 0 or 1, these sets of rational points have been verified to be complete using Chabot's method, or Coleman's sort of refinement of it. But for curves of rank 2, 3, or 4, and 4 is the highest rank that occurs in this data set, the list just says known rational points. And the reason for this is that we don't have a proof that these are complete. It's just the points that have been found where you search for rational points up to some given bound, and probably it's complete, but we don't know that. So my goal here was to look at some subset of these and to see how far we can get with a certain set of techniques. See how often can we actually compute this set of rational points provably. Well, provably conditional on GRH, as we'll see. So if the rank is greater than or equal to the genus, then the issue that obstructs Chabot's method is that the set of rational points of the Jacobian could just be p-adically dense. And so then the question is, what do we do? Well, one approach is if the Jacobian has a quotient that satisfies rank less than dimension, then we can use that map in place of Abel Jacobi. And in the case where this is a restriction of scalars of an elliptic curve, or equivalently, if our curve has a map to an elliptic curve defined over some extension of the base field, this is called elliptic Chabot, and this is also implemented in Magma. Another method, which I'll just say in this one line, but this is something that I also work on, is the non-abelian Chabot method. This was originally due to Min-Young Kim, and it's been worked on and refined by many other people. And the idea is that if you replace the Jacobian with some object that comes from a non-abelian piece of the fundamental group, then you can get further and you can deal with curves of higher rank. In the sort of what's called quadratic Chabot that goes like just one step in the lower central series beyond abelian Chabot, this has been implemented in some cases where the rank is equal to the genus. And this is a very active area of study, which I'd be happy to talk about later, but I'm not going to say anything more about here. And finally, another approach is descent. You take some collection of covers of the curve such that if you can find the set of rational points on each of these covering curves, well, every rational point on the base curve comes from one of these. And if the geometry of these covering curves is easier in some way, then you can sort of use this covering map to transfer the problem from your original curve to some other set of curves. And so the approach that I'm going to discuss here is using descent in combination with elliptic Chabot. So in particular, the descent we're going to use is two-cover descent. So you embed the curve in the Jacobian by the Abel Jacobi map. I'm going to assume from now on that we always have a rational base point, which we'll assume in fact to be a rational Weierstrass point. Then we have a degree 2 to the 2g étale covering of your curve, given by just pulling it back by multiplication by 2 in the Jacobian. And one can compute, and when I say one can compute here, I actually mean like this is explicitly feasible to compute, at least in the cases we're going to be talking about here, a finite set of twists together with maps such that every rational point of the original curve comes from a rational point on one of the covering curves. And in the case of genus 2, this is a genus 17 curve, which is a maximal unramified abelian 2 covering of the original curve. And in fact, what is nice here is that in the genus 2 case, the Jacobian of this genus 17 curve has a very nice structure. So over Q bar, up to isogeny, so of course you've got the, let's see if this works. Yes, you've got the Jacobian of the original curves, this 2-dimensional factor, and then the remaining 15-dimensional part is in fact geometrically a product of 15 elliptic curves. So this gives us lots and lots of potential to apply elliptic Chabot-T. So the approach to writing down explicit equations for all this that I took is using Kummer surfaces. So Brown and Stoll used a different approach. They gave an explicit description of two-cover descent for hyperelliptic curves. The variant of this that I implemented in Magma for genus 2 quintics uses Kummer surfaces. So when you have the Jacobian of a genus 2 curve, what you do is you quotient by the -1 involution. And then this gives you 16 simple nodes corresponding to the 2 torsion points of the Jacobian. If you blow up at those, you get a K3 surface that's called the desingularized Kummer surface of the curve. So this is a K3 surface. It can be written down explicitly as the intersection of 3 quadrics in P5. This is all a very explicit picture. Flynn, Testa, and Van Leeuwenhoek, in fact, gave explicit equations not just for this, but also for all of its twists in the same sense of twist that we need for descent. And so these are like quotients of twists of the Jacobian. It's all a very explicit picture. You can just write down these equations. And now if you take this genus 17 cover, so you have the original curve, you take this genus 17 cover of it in the Jacobian, and now you map that down to the Kummer surface. Well, if you just count things using Riemann-Hurwitz, you see this is in fact a smooth genus 5 curve. And I can show this is canonically embedded by a hyperplane section that you can just write down of this Kummer surface in P5. So you have these genus 5 curves that are occurring as hyperplane sections of a Kummer surface or a twisted Kummer surface. So just to illustrate this, so I'm sort of suppressing the twists from the notation just to keep things simpler. So here's the picture, right? We have the multiplication by 2 map on the Jacobian, and then this descends to a multiplication by 2 on the Kummer surface. And here we have the original curve with its standard map down to P1. We have the genus 17 covering curve, and then this maps down to the genus 5 curve, which also covers P1. And so what I did then is compute explicit formulas, not just for this, but also for this covering map and the branch locus. And so sort of made this whole left side here very explicit. Now let's also make the maps to the elliptic curves explicit over the field of definition. So if we write our curve as like y² equals quintic, and we sort of pick one root of this over a number field, which is generically quintic, and then we take the remaining degree 4 factor, well, the elliptic curves are going to be Jacobians of this genus 1 curve, which is some twist of y² equals this quartic. And the quadratic twist parameter here, we can actually give an explicit formula for as well. It's just an explicit polynomial in terms of the twist parameters. And we can also write down an explicit formula for the map from our genus 5 curve to this genus 1 curve that gives a factorization of the multiplication by 2 map. So it's all a very explicit geometric picture here. And so this is exactly the data that we need in order to apply the elliptic Chabot-T method to this genus 5 curve. And then the idea is, well, if we can compute the rational points on this genus 5 curve, then we can pull those back and get a complete list of rational points on the original genus 2 curve. And I also showed that, in fact, if you have this whole picture here, the Jacobian of this genus 5 curve Z is just isogynous to the restriction of scalars of that elliptic curve. So we also now have a description of the Jacobian up to isogeny. I've just written down the version for F irreducible. It's similar for F reducible, just a little more complicated. And then, so I implement all this in Magma. So we take a genus 2 quintic curve as input. We compute the list of twist parameters and construct all these curves and maps I just described. We search for rational points on each Z. If we don't find any rational points, we check whether Z is locally solvable. If it is, currently the algorithm that I've implemented just has to give up. In the future, I'd like to just implement a version of the Mordell-Vaisive that can actually prove that there's a failure of the Hasse principle. And then if we can continue, we then attempt to compute generators for the Mordell-Vaisive group of this elliptic curve, which in practice is the bottleneck and also requires assuming GRH to be feasible. And then we run elliptic Chabot-T to compute the set of rational points and then pull everything back to get a complete list of X coordinates for rational points of the original curve. So that's all a little bit abstract. Let's actually see this in action here. So we've got this curve with this given equation. It has 7 known rational points. And let's actually verify that it has exactly 1 rational Weierstrass point. So let me share this demo here. Great. So first off, we just import the code. And here's our original curve. For technical reasons, we want to use a sextic model just to make it match up with the equations for the Kummer surface. We compute our list of twist parameters. Here they are. They're represented by polynomials. Oh, make it bigger? Great. Is that good? Cool. All right. Continuing on, we now are going to compute the models of these curves. And so you can see here's the equations of these curves. It's all just very explicit, given by 3 quadrics in P4 after we've taken this hyperplane section. And we verify, yes, indeed, these are all genus 5. And we compute just by searching, well, here are the rational points we find, right? So this one has this one has 3 rational points. This next one has, this one has 1 rational point. This next one has 2. This one we don't find any, and this one we find 2. And then here we have the X coordinates after you project down by that map. So what we want to show is that this is the only possible list of X coordinates that can occur on the curve. I also just want to show you, like here is just lifting these back to the original curve. So you can see, okay, so one of these is just the rational Weierstrass point. This one lifts to 2 rational points. This one doesn't lift to any rational points. This lifts to 2, this lifts to 2. So in total, we do indeed find 7 rational points coming from these X coordinates. Now we have to prove that, in fact, those are the only rational points on the genus 5 curves. So we construct the curve, we construct the elliptic curve now and the corresponding maps. And now we want to compute the Jacobian, or excuse me, the Mordell-Vaisive group of the Jacobian here, of this elliptic curve. And so that takes a few seconds. As I mentioned, this is generally the bottleneck. So it's chugging along. There we go. So this Mordell-Vaisive group is Z squared. Now we construct the covering map from the elliptic curve to P1. So you can see the equations are not bad. It's just something you can write down. And now we run elliptic Chabot-T and see, yes, we just get this 1 point. So that's one twist done. Second twist, similar thing. Okay, we've got the equations for the curve. We construct the elliptic curve. And now we're going to tug along for a bit and construct the Mordell-Weil group. I think this one's another z squared, if I remember right. We'll find out in a few seconds. Yeah, another z squared. And I'm just going to set this to, whoops, not that button, set this to running on the rest. Okay, so now we do this curve here. And let's see here. Yes, we still need to run Chabot on this one. So now we find these 2 points. So those are the only 2 points on this one. Again, assuming GRH here. Third curve, we construct the curve, and look, we don't find any rational points. So now we want to see, okay, is this thing locally solvable? So here's our bad primes, and the answer is no, this is not locally solvable. In fact, it has no Q2 points. It has no 2 adic points. And so therefore, there's no rational points, so that one's done. And now finally, we just run things for the last curve here. This thing's just going to run all the steps. Here's the elliptic curve. I believe this one's a z cubed, if I remember right. So we're going to get a rank 3 one here. By the way, note that we can handle using elliptic Chabot rank up to 4 because the degree of the number field is 5. And in elliptic Chabot, there's a sort of thing where we're essentially working with the restriction of scalars, so it's really like a 5-dimensional abelian variety. So the equivalent of rank less than genus is indeed rank less than 5. And so yes, we get these original 2 points. Now we put together all the x coordinates, and there's our original list. So yeah, that's it for the demo. You just stop this and go back to the slides. Couple last remarks. So in order to run this on a big data set, I took all 7,692 genus 2 quintic curves in the LMFDB that have rank at least 2. And I ran these algorithms on the Boston University Shared Computing Cluster, which is a roughly 21,000 core Linux cluster. And so I was able to run these at once, and here's the summary of the results. So 13.6% of the time, assuming GRH, it just succeeds, no caveats. About 27.6% of the time, we run into this issue where one of the twists seems to have no rational points, but we can't prove it because we don't yet have an implementation of the Mordell-Weil in this version. About 10.4% of the time, the Mordell-Weil rank is too high. So, this is where we get something of rank 5 or higher, or in the reducible case, it might be like, oh, it splits into a degree 3 and degree 2 factor, and maybe they both have rank 3, so we're out of luck, that sort of thing. About 29.5% of the time, Magma was unable to compute one of these Mordell-Weil groups. That's the real computational bottleneck. And about 22% of the time, I set some sort of limit on how long I would let these just chug away before cutting off the computation. So we hit like some sort of time or memory limits. And again, this is almost always due to difficulty computing the Mordell-Weil group. So for all of these, I recorded detailed data in JSON format that sort of records all the intermediate computations and any obstacles that were encountered. So, if anyone else wants to sort of start where this left off, improve on any part of this method, the computations that were already done don't need to be redone. And the results where it succeeded, these are going to be incorporated soon into the LMFDB, so that we can, mark things as known conditional on GRH rather than just conjectural rational points. The other thing is probably the biggest thing that would help for addressing this bottleneck is if we could get an implementation of 3 or 4 descent for elliptic curves over number fields, because 2 descent is great, but it can only get us so far. And the coefficients on these elliptic curves are big enough that, a sizable portion of the time, 2 descent just wasn't enough to actually find generators for the Mordell-Bay group. So I'll end with just a few links. Here's the preprint. The code and the raw data are both available on GitHub, and I will stop there.